All right, good day, everybody. Wherever you are, I'm so happy and I'm so excited to be bringing this to you. It's a very, very big package from CMRC, Creative Minds Real Concept. And I'm most privileged to be the innovator, the initiator of this program. It is a very, very big success to bring this to you. Free Success Project 2025. And this year, I am so happy. We have amazing facilitators, persons who are selfless, who are passionate, who are explicit in every ramification of their discipline, and they will blow your mind. So I want you to keep your tabs and start watching these videos and get excellent results and come back to tell us, and we'll rejoice with you. God bless you.
Good day, everyone. Welcome back to this new episode on chemistry. So I remain Folaranmi Israel Olaoluwa. So in the last video, we started talking about nuclear chemistry. So, and then under nuclear chemistry, I made some important points, of which radioactivity was one of them. So I was able to define what radioactivity is. So, and then the types of radioactivity we have, which are what? Natural and then artificial. So I made us to understand that natural radioactivity is a kind of spontaneous form of radioactivity. So it does not involve like humans to do it. So you just find a radioactive substance breaking down by itself, like disintegrating by itself. So, but under artificial radioactivity, you need to bombard a substance which is normally not radioactive. So you bombard them with subatomic particles, which are usually high energy moving particles, like neutrons. So by bombarding them with those particles, they become radioactive themselves. So after becoming radioactive, they can now undergo disintegration. So the only difference between natural and artificial is that there's a kind of human effort being involved in artificial radioactivity by the bombardment of substances that are not normally radioactive. So we bombard them with what? Particles. So they become radioactive. So, and then under natural radioactivity, I was able to list for you guys that we have three examples under them, like three types of natural radioactivity. We have alpha, the alpha emission. We have what? The beta emission, and the one that deals with the emission of what? Gamma rays. So we call alpha and beta, we call them particles. But we don't have, for the case of gamma, they are not particles, they are only what? Rays. They are only rays. So now, I told you that under alpha emission, you have, what happens there is that a substance, a radioactive substance, spontaneously breaks down, and then an alpha particle is being liberated. So for an alpha emission, you have alpha particle being liberated. So under beta emission, what happens is that you have beta particles like being liberated. And then under gamma rays, what happens is that you find a radioactive substance like it emits a gamma ray, but there is something that's unique about gamma ray. So when I get there, I will explain that to you. Now we've talked about alpha rays. So the next thing is what? Beta. So when we are talking about beta rays are like they are streams of electrons. They are streams of electrons. So when we are talking about beta emission, the main thing that happens in beta emission is that you find a radioactive substance which disintegrates and gives another substance. So you find a radioactive substance breaks down and gives another nuclide in which its atomic number will increase by 1. So now, for example, let's say you have a radioactive substance S now with atomic number 10. So if it undergoes beta emission, what is going to happen is that the daughter nucleus that you are going to have, let me say Y, the atomic number will increase by what? 1. So X has an atomic number of 10, but after undergoing beta emission, it will have what? Atomic number of 11. And then under beta particles, there is a sign that you usually have in front. You always see something like this. You write something like this, -1, 0. This -1 that is here under this Greek symbol is for it to balance up the equation. So when you have a beta emission, let me give you an example now. Let's say we are talking about, let's say sodium Sodium, the atomic number of sodium is 11. Let's say sodium 24. That's a radioisotope of sodium. So if it undergoes beta emission, what is going to happen? What will happen is that the nucleus you are going to get now, the atomic number will increase by what? 1. So before, the atomic number of sodium here is 11. So you are going to get another nuclide with the atomic number of what? 12. So this will be what? That will be Mg 24 and then what? 12. With the beta particle that is being released, you represent it with this Greek symbol called beta minus 1, 0. Such that when you add this on the right hand side together, you get what is on the left hand side. So 12 plus minus 1, you are going to get 11. 24 and 0, you are going to get 24. So one thing that is unique about beta emission is that a radioactive substance like emits radiation, and then what? It liberates a beta particle. So beta particles are streams of electrons, and then after a radioactive substance emits a beta particle, what happens is that the daughter nucleus, that is what is being formed after the emission of radiation, is going to have an atomic number with an increase of 1. So if you are starting with a radioactive substance that has atomic number of 3, eventually after liberating a beta particle, the atomic number will be what? 4. So the another substance is going to have atomic number of what? Of 4. So that's what beta emission is all about. So, and then we have characteristics of beta particles. One of them is that beta particles are negatively charged. They are negatively charged. So there is this question that is always in your UTME. They usually repeat. You see them drawing something like this. This is like a magnetic field. You just draw it, and then you find, let's say there is a magnet here. Are you getting me now? So let's say this is the positively charged side, and this is the negatively charged side. So you can see them drawing something like this. So to the positive, you can see something like this, and then something like this. They cannot ask you what type of particle are represented by these following letters A, B, C. Now this is just a kind of magnetic field, and then trying to see how those rays and particles are deflected. Don't forget, under alpha particles, I told you that alpha particles, they are what? Positively charged. Alpha particles are positively charged. That is to say, when you bring them to a magnetic field, what happens is that they are deflected towards what? Negatively charged pole of the magnetic field. Don't forget that like charges, they repel. Unlike charges, what? Attract. So if an alpha particle is positively charged, that means it will be what? Deflected towards the negatively charged pole. So beta particles are negatively charged. That means they will be deflected towards the what? Positively charged pole of the what? Magnetic field. So now, under this, if this is plus, this is the positive side, this is the negative side. Now, what type of particle do you think will deflect to the negative side? That is the what? Those that are positively charged, because they must obey the rule of what? Unlike charges attract. So the positively charged particles will deflect towards the negatively charged pole of the magnet. So that means this one C will be what? Alpha particles is represented by this sign alpha. So positively charged species or positively charged particles, they will be deflected towards the what? Negatively charged pole of the magnet. Also, this one that is going to the positively charged pole, that will be what? The negatively charged particles. So to the positively charged pole, positive side of the magnet, negatively charged particles will move there. So that's to tell you that this place here will be what? It will be beta particles that are moving here. Now, the one that is left undeflected in the field, that will be the what? The gamma rays. So that will be the gamma rays. So for alpha particles, they are positively charged. That means they will be deflected towards the negatively charged pole of the magnet. For beta particles that are negatively charged, that means they will be deflected towards the what? Positively charged pole of the magnets, in order to fulfill the law that unlike charges, they attract, while like charges, they repel. Are you getting me now? So that's that about beta emission. So one thing that is unique to gamma is that under gamma emission, they are not called gamma particles. They are not called particles. So they are called the rays because they don't have any mass. So alpha under alpha emission and beta emission, what are liberated there, they are called particles because they are what? They have mass. But gamma rays, gamma are not, under gamma emission, what is being released is not called particle because what? They don't have mass. So they are better called rays. So you can't say anything like alpha rays, beta rays. No, you only hear alpha particle, beta particle. But when it gets to gamma, what do you see? Gamma rays and not gamma particles. So characteristics of gamma rays are, gamma rays, they are like, they don't have any charge. So they are neutral. You know, alpha particles, they are positively charged. Beta particles, they are negatively charged. But gamma, they have what? They have no charge. So they are neutral. Gamma rays have no charge. So, and also they are neutral. And then when you place it in a magnetic field like this, they are not deflected. They just remain undeflected in the field. So when they draw something for you like this straight line, the ray that is represented by this straight line, that will be the what? The gamma. That will be the gamma. It is not deflected at all. It's not deflected. If it were to be alpha particle, it will deflect towards the negative pole. If it were to be beta particles, they will deflect towards the what? Positive pole of the magnet. But for gamma particles, they remain undeflected because they have no charge. So they are not moved, they are just there. And then another property of them is that they move with the speed of light. They travel with the speed of light. And I know that in secondary school, you know that speed of light is what? 3.0 times 10 raised by what? 8 meters per seconds. That's the speed of light. So gamma rays, they move with what? The speed of light. So what happens in gamma emission is that, now let me give you this example. You know, for under alpha emission, when a substance undergoes alpha emission, what happens is that an alpha particle is being liberated. And then an alpha particle is in the form of what? Nuclei, is in the form of helium nuclei. And then for beta particles, what happens is that the atomic number of the daughter nucleus that we form, it will increase by 1. It will increase by 1. But for gamma rays, if a substance undergoes gamma emission, what happens is that nothing happens to the mass number, nothing happens to the atomic number. It still remains the same, but it will liberate energy and gamma rays. So you can have something like this. Let's say you have uranium 238, mass number 238, atomic number 92. If it undergoes gamma emission, you are still going to get what? The same thing. Uranium 238, 92, plus what? Plus gamma ray. This is your gamma ray, plus gamma ray, and what? Energy. So when a substance undergoes gamma emission, nothing happens to the mass number, nothing happens to the atomic number. It's not like alpha emission and beta emission that something changes. This one just remains the same. It remains the same. So that's all about natural radioactivity. Now let's move to artificial. So artificial radioactivity occurs when you bombard substances that normally they are not radioactive. So by bombarding them with high energy particles, they become radioactive, and then they break down spontaneously. So for example, now let's say sodium 2311 is not radioactive at all. It's not. But you can convert this to a radioisotope by bombarding it with neutrons. So one of the energy particles that you can bombard substances with to make them radioisotopes are what? Neutrons. So if you bombard this with a neutron is of this form, N10. This is how a neutron is, N10. So anywhere you see this thing, this is a neutron. So what will it form? Plus, that means you have 23 plus 1, that will be 12. That will give rise to what? Sodium 2411. This is a radioisotope. Normally sodium, the normal sodium that we know, is not radioactive. But after bombarding it with high energy particle, and the high energy particle we are using here is what? Neutron. So you get what? A radioactive sodium. So this is what artificial radioactivity is all about. You bombard particles. You bombard substances with what? High energy particles to make them radioactive. So that's that about artificial radioactivity. Now let's move to nuclear fission. As the name implies, when we are talking about fission, we are talking about something breaking down, something big breaking down into smaller particles. So nuclear fission is the breakdown of a large nuclide into what? 2 or more simpler nuclei. So when you have a very large nuclei breaking down into simpler forms, that's what nuclear fission. So when you are talking about nuclear fusion, from the word fuse, like you are bringing together, is nuclear fusion occurs when you bring like simpler nuclides, when you bring them together to form a what? A large or a larger nuclide. So when, for example, now under nuclear fission, let me give you an example. Let's say you are combining deuterium. Deuterium is an isotope of hydrogen. So you have deuterium. This is deuterium D. It has a mass number of 1, atomic number of 2. And then you are combining this one with okay, let's say you are combining 2 deuterium molecules. This is another D, 2, 1. In some textbook, you might not see this D. They can just put hydrogen. Okay, let me just replace it with hydrogen. We are still talking about the same thing because deuterium is an isotope of hydrogen. So if you combine these two together, it's going to give you something like this helium nuclide 4, 2. Now look at this. This is a very simple nuclide. Deuterium, you are combining with another deuterium molecule to give a much larger nuclide. So this is what fusion is all about. You are fusing together, bringing two simpler things to form a bigger one. That's what fusion is all about. Now, if you are talking about fission, that means you have a very large nuclei and then you are breaking it down into what? 2 or more simpler nuclei. So breaking down into 2 or more simpler nuclei. So now if you have something like this, let's say you have uranium 238 92. Let's say you now break this one to thorium. This is thorium 234 90 plus helium 4, 2. This is a kind of nuclear fission because this lone radioactive substance is breaking down into 2 or more other substances, other daughter nuclei. So fission is about breaking down, while fusion is about what? Coming together. So when you see your question and then they give you that, okay, the nuclear reaction whereby 2 or more simpler nuclei come together to form a bigger one, that is what? Fusion. But if the question says a nuclear reaction whereby a large nuclei breaks down into 2 or more simpler ones with the release of energy, that's what we call what? Fission. Now let me give you example. I know that you must have heard of all these your hydrogen bombs everything. For those of you that watch movies very well, you have atomic bombs, hydrogen bombs, those 2 type of bombs. So those bombs, the way they manufacture or design those bombs is based on the principle behind nuclear fission and nuclear fusion. For example, now if you are talking about atomic bomb is formed as a result of a chain reaction that occurs in nuclear fission. So they might ask you a question, UTME, I've seen it before a lot of times, that the question will say that, okay, atomic bomb is as a result of what? The answer is what? Nuclear fission. Fission. Nuclear fission. So the process or the mechanism that brings about the manufacture of atomic bomb is what? Nuclear fission. So when you break down a large nuclei into simpler ones, that's what we mean by nuclear fission. So you form atomic bomb through nuclear fission. And then the second one is hydrogen bomb. This one is hydrogen bomb. From the word hydrogen, that means it's being made from hydrogen or one or more of its isotopes. So hydrogen bomb is formed as a result of a nuclear fusion reaction. Don't forget what I said in the first time. Nuclear fission gives rise to what? Atomic bomb. So if you want to form an atomic bomb, you need the mechanism of reaction is what? Nuclear fission. When we are talking about hydrogen bomb, then the mechanism of reaction is what? Nuclear fusion. So in hydrogen bomb, two molecules of deuterium come together. And then a chain reaction is being initiated. So you find something like this, HH21 plus 21H to give helium nucleus, and then you have, when you bombard with protons like that, it leads to a chain reaction, thereby providing the energy needed to fuse other hydrogen molecules together. So this kind of reaction, this is nuclear fusion reaction, and it gives rise to what? It gives rise to your hydrogen bomb, while your atomic bomb can be formed through a nuclear fission reaction. So I've made two important statements. Your atomic bomb is formed from what? Nuclear fission, while your hydrogen bomb is formed from what? Nuclear fusion. So that's that about nuclear fusion and nuclear fission. So I talked about radioactive decay in our last class, and I talked about half-life. So let me bring it to your remembrance that half-life is the time taken for what? A radioactive substance to decay or to degrade or to disintegrate into what? Half its initial or original value. So the time taken for a radioactive substance to decay to half of its original value, that's its half-life. So if a radioactive substance has a mass of 10 grams, and then after 2 days it degrades to 5 grams. You know that 5 grams is the half of 10 grams. That means 2 days is the half-life of the what? Of the substance. So the time taken for a radioactive substance to degrade to half its initial value, that's what? The half-life. That's the half-life.
Be sure to link up with us, message us, seek out our email, send us messages for further questions and mentorship after you have seen these videos. I'm very happy to say this again, that it's a time for you to move on and succeed. It's a free success project 2025. Bless you everywhere that you are. Again, my name is Emmanuel Aderoju Adeyemo from Creative Minds Concept.